Okay, so let's get started. Welcome to lecture 13, and hopefully the last lecture in this course. So we continue our discussion on the 2-to-2 games theorem. So the 2-to-2 game theorem, as we stated last time, is basically we want to prove the hardness of label cover, but where the constraints are of a very particular type. They are not as specific as the UG constraints, where the constraints, we check the local view of the constraint graph, it's a permutation matrix, but this is sort of a 2-to-2 matrix. And last time we had sort of said that the core of this is going to be a Grassmann linearity testing result. So let's just recall that from last time. Recall Grassmann linearity testing. So X is some k-dimensional F2 space, vector space. And in this linear testing, we are going, and we want to check if a given function is a linear function on this space. So you can of course specify the linear function by just giving k bits. But that's not how we are going to do it. The Hadamard linearity testing was specifying linear function by giving the evaluation of the function at every point. But what we will do is we will give the restriction of linear function on every L-dimensional space. In particular, the set of points we are going to be looking at is this Grassmann XL, which is basically the set of L-dimensional subspaces of these. So the input is explicitly it is explicit input is x, k, x, and l. The oracle input is this function f going from grxl to 0, 1 to the L. So we'll assume that there's sort of a canonical, for every element space, there's a canonical basis. We'll pick it upfront, and 0, 1 to the L is basically going to give me the linear function on that basis. That's one way of specifying the linear function. And what was the test? The test was this very simple thing, that is pick random L prime dimension space in Grassmann X L minus 1 at random. Pick L1 and L2 from Grassmann X L such that L1 intersection L2 is L prime. Query F on L1 and L2 and accept if F restricted to L1 on then F on L1 when restricted to L prime is the same as F on L2 when restricted to L prime. And here by here I mean the linear, look at the linear function, that linear function is restricted, because I obviously invested.
So L1 and L2 are also chosen randomly.
L1 and L2 are chosen randomly from there. So yeah, so in some sense, in the language of these test cases, you look at the L prime, they are two, but they are not chosen independently because their intersection has to be to this one. If they are chosen independently, they can be a lazy. You could have chosen L1 to be equal to L2. We'll always ensure L1 is not equal. That's a very small probability, but so this is what we'll do. And the key thing last time we noticed was this fact that this test, the usual sort of test analysis doesn't work, and we had several sort of counter examples to this, and we said, and the counter examples basically arose from the fact that you could choose, you could pick you could pick both a zoom from below and a zoom from above. That is basically you could choose a small dimensional subspace Q and a large dimensional subspace that is one with 4-dimensional small Q under W, and choose linear. Just so now you restrict yourself to linear subspaces which contain Q and which are contained in W. And for every, and you choose several such QW pairs, hopefully non-intersecting. Hopefully, when I mean QW pairs, I'm looking at linear subspaces contained in them. Hopefully, the set of linear subspaces contained in these QI/WI pairs are all non-disjoint, but they can cover an alpha fraction of the entire space of L-dimensional subspaces. Now, for each of them independently, you could have chosen one global linear function and answered consistently across it. Because this graph, the Grassmann graph, does not expand, that these are non-expanding sets, this test will individually, each small component will pass the test, and there are very few edges that are going across this one. Therefore, this will pass the test with a reasonable amount of probability. And hence, the typical product boundary analysis for this test will fail because there's really tiny parts, a large number of tiny parts, each one which are all non-expanding in the set. Almost all the, if you look at all the previous tests that we have done, the Hadamard test, the BLR testing, or the low degree testing, if you draw the graph between a line and another line based on an intersection, or a triple and another triple, or one point and another point if they participate in a Hadamard, this graph, if you see, will be an extremely expanding graph. Whereas out here, we are stating that there are really small sets that don't expand. That's the big difference between those tests and these tests. So what's the test I'm talking about? The low degree test, that is either draw the test between 2 points if a line contains them. Now notice this is a complete graph. Or take 2 lines, or this is a complete graph in this case. Hadamard test is also a complete graph. So these graphs are extremely expanding graphs. These are not exactly the graphs. The BLR graph. The BLR graph. Basically, you have to move from one test to another test, is basically what I want to do. So basically, the line thing, you move from one line to another line. One line to another line, of course, you can't move arbitrarily. That is, you only move to another line and it intersects at a point. But notice in 2 steps, you can move from one line to another line. So the diameters of these graphs are all very small. And you can also show that the diameters are not they're even better than expander. They're actually constant. So this graph is not even an expander. There are small sets which just fail to expand. And that's the reason why the analysis for this work is non-trivial. We can't get a statement like what we had got previously, but what you can get, the best you can get is the following, which was conjectured in the DKKMS result in the sequence of the first 3 papers in this line, and the last paper basically proved this, and this was basically the theorem about, this is the theorem which we said last time, this is theorem about the non-expanding sets in the Grassmann. Basically, this is the theorem which we have. This is the final. This is what we said last time. If there's a non-expanding set, we can explain every non-expanding set. Every non-expanding set basically arises from one such, from basically from a zoom from below, zoom from above, etc. This is what we want in the non-expanding set. What? But of course, this is not an analysis of the test that we. This is just talking about which are the non-expanding sets. So what did KMS, the final paper KMS 2 show? We had seen that there are counter examples for why this test may fail, and the reason that it fails because there are these tiny sets which don't expand. What KMS 2 showed that we have full understanding of what are all these sets that don't expand. Now, given this, can you now go back and do the theorem? This is what DKKMS did. This is a very simple translation. I will skip it for this, but it's not hard to DKKMS do. So, assuming the above hypothesis, they showed that for all delta.
So here, what is the statement that AC is non?
Huh?
You are just saying AC is non-expanding, but
No. Already it doesn't say S is small. There is any non-expanding set has to if. But by the way, I'm given if X is a large. So by the way, S need not be a small, super small, because we could take several non-expanding sets, put them together, they will be non-expanding. Huh? So S need not be small. I'm saying that is the example which we showed a small non-expanding set, but I could have just taken a union of several of these. This need not be small, but it will be non-expanding. And notice that the conclusion basically addresses that. It says, suppose there is an S which is non-expanding. I don't care of the size of set, but there will be the zoom in and zoom out. Now I'm going to a very small part of the graph. There, that set looks like this. Now possibly there's another movement that also it looks like this. So I'm sort of moving into. So this explanation is not explaining all of this. It's explaining this in a really tiny part of the graph. It doesn't explain what possibly what one should do. We'll come to that later. This explanation, notice, doesn't explain the complete non-expansion of S.
say we will use it for S minus S AB. And
Ideally, we would like to do that, but there are ways to. So, in the usual, in the low degree test cases and all, whenever we could explain something smaller, we would peel this part out and then see if the still is not expanding, then it's explained by some other zoom. You keep doing this. So usually on that list will be a constant sizes, constant which only depends on delta. Unfortunately, in this case, that's not going to be the case. That is, this can actually be the number of zoom ins and zoom out that you want to explain the all of S can be a function of L, not a function of delta. So there are these various orders of the first delta is a constant, then L is large enough, then K is even larger than L, then N is above this. Each of these are sort of things which are going off to infinity, but at large, each one at its own rate. Delta is going. But anyway, it doesn't explain all of this, but we will come to that question right now. But let's take the hypothesis. What does that give for the test? That gives the following thing for the test: that there exists integers. Exists an integer r greater than 0, greater than or equal to 0, and an epsilon and 0, 1, such that for all sufficiently large L and K larger than L, the following holds. If probability that what is this right? This L1, L2, L prime, following holds is if f of L1 intersection L prime is equal to f of L2 restricted to L prime. If this is larger than delta, if the Grassmann test passes, if then there exists Q in W subspaces of X such that the dimension of Q plus the codimension of W is less than equal to R. The R is some fixed constant based on delta. So that if you zoom into this part of the graph and the function f on W2, and we'll just say that we just call it and a linear function. Linear function W and linear function f on W such that the probability, now when you pick an L not completely at random, but from this Q and W, and also dimension of L is L, that f of L is actually f restricted to L. This is at least significant. And from that to this is an easy transformation. I'll skip that. That's everything I'm going to skip. But basically, it says any reason the test passes, you can explain it by some student. But once again, the same question happens. This is not explaining the test on a large part. It's explaining the test on a really tiny part. But I would like to explain the test on a reasonable part of this one. And the reasonable part we'll explain is only reasonable. It will be a function of L, not a function of. No, so eventually, if you want, so let's look at this. If I want to now use this in and eventually construct a PCP out of this, I want to now sort of say the two provers. So for whatever the two provers, they are going to answer, they are going to somehow agree on this one. But the point is that there is no single function that can agree on. Each zoom in, zoom out has several such things. So possibly you'll say, I'll do a union bound over these Q's, the number of possible explanations, and hopefully that error I can handle. This is what we did in the Adobe.
This is not. It's true here also.
No, it's not. It's not true. I won't be able to do the union bound. But there are several issues over there. Firstly, you don't get an F on the entire space. You get an F even when you do. Even when the two provers have agreed on a particular F, this one, the F is only on a W. It's not on the whole space. So how are they being good answer? There, but of course, the point you say is the fact that the W is only has codimension, constant codimension. Therefore, F on the global space, you only need a few more bits of predetermined. So the two provers will sort of independently get these extensions, and hopefully, because it's only a constant number of bits that they have to guess, they will get the same object. So then several things, but first let's write a statement about how many Q's that we can explain. So the statement which we are going to have, which we can prove from this, is the following modified statement. You have a question? Notice for the two provers to answer consistently, if you are going to use this,
the one that gives the left side and the one that gives the related side. So
we have actually said who are the two provers. I'm going to construct using this guy a two prover, which is a two prover system, on which I'm going to put the 2 to 2 this one. So the two provers over there. The two provers over there. So they will have to answer. So basically, how will I will come up with a reduction from some NP hard problem to a label cover instance in which the constraints have this 2 to 2 feature, and the inner verifier of that will be invoking the Grassmann test. And how will the soundness proof of the reduction go? You have to say that if this object if this guy has an assignment which satisfies more than delta fraction of the constraints, you want to this one. That we will see because it satisfies delta fraction of the constraint, there will be several, because they will be invoking the Grassmann test, there will be several Grassmann tests which are all passing the probability delta. But because of this, you want to say that because they are passing, there must be these functions f that are explaining them on each of these rooms. And from these functions f, you want to actually eventually produce a contradiction to the original problem we started off with. So how do you basically the two provers have to eventually come up with some function f going to do. I'm not saying so I'll give you the reduction, you will see later on, but what I want to say, okay, let me change the order in which I want to do. Let's actually go to the reduction. How I'm going to use this as an inner, use this test as an inner object in the reduction, and then in the reduction we'll use this theorem. So what I wanted to do is this theorem is not sufficient, we have to have several further modifications. So I wanted to do a modification, but we'll see the reduction and then come back to the modification. So what is the reduction? So let's see. The reduction from, so we are going to reduce from gap 3 ln 5. So we're going to take 3 ln, okay, that should not follow 5, 3 ln 2 only, 3 ln 2, that is linear equations on GF2 with 3 variables each. And the gap will actually, I don't need a 1 minus epsilon half gap. I'm just going to work with, but let me just say gap 3 ln 2 gap 1 minus epsilon delta. What was this? We had this. What did I call it? Let us see. What was the notation I used last time? Yes, we'll see, but the alphabet size being F2 here. Let's see either gap even to instance. I'm going to make a couple of assumptions from this. Firstly, every variable appears in exactly 5 equations. And we resort to it's a known fact that it is NP hard gap 1 minus epsilon 3/4 3 ln 2 with each variable in 5 equations is NP. So this is, you start off with Hasad's, this construction, you can sort of do the regularization, make the vertex side regular, you lose the half becomes something else, but I don't care. All I want is 1 minus epsilon versus some fixed constant bounded away from 1. So this will be a starting point. So this instance P has variables x1, x2, xn, and it has a bunch of equations e1, e2, en. In fact, e1, e2, en will be exactly 5n by 3 or so. Equation of the form x11 plus xi1 plus xi2 plus xi3. The IT equation will be of this form equals en. So now I need to tell, and from this I'm going to construct this is something which we did in the last part. What we will do is we are going to construct a two-tower system in which U and V. Each guy here is going to be a set of K equations. And each guy here is going to be sort of something like 3K minus 2 beta K variables. And if you recall how we did this, this is all sets of K equations. And this is, now take the K equations, look at the each equation, you toss a beta biased coin. So if it comes up heads, that is with 1 minus beta probability, retain all the 3 variables. Otherwise, just pick one of the variables at random and give them, throw off the other. So therefore, you have this, you have the structure, but we're going to do some more tuning on this. So K is constant. K is a constant. So N is the global thing, K is really constant. And it's going to be very important if K is constant. So we are going to put only, among the set of, the U belongs to U, we'll only put certain things which are called legitimate. And what does legitimate mean? The first thing we want is, so you're given a set, this is a set of K equations. We'll assume that all the 3K variables that appear in this K equation are distinct. It's actually 3K. And because K is small, the number of such non-legitimate guys will be extremely small. So if we happen to pick such a thing, we'll just toss it and that won't add anything to the statistical distance to the whole. So we'll assume that all 3K variables in U are distinct. In addition to this, we're going to assume one more thing, that is, take any equation, not necessarily something appearing in U, take any other equation, so it has some xi, xj, xk. So let's take two of these variables, xi and xj. I want to say there is no U in which I appears in one of the, if I appears in one of the equations, j should not appear in any one of them. It could appear if I just pick this very equation, ijk, but otherwise it cannot appear. If j appears in one of them, I should not appear this one. And this is all, you can do all of this because so all I want to state with the following sort of. For all pairs of variables. So take any equation E in U. If X belongs to if Xi and Xj both participate in E, then consider a pair of variables Xi and Xj such that where variables X and Y, so that X belongs to EI and Y belongs to EJ, I not equal to J. Then there is no equation E anywhere such that X and Y participated.
The X can participate in only one, at most one equation.
No. This is no equation, not just in U, in the whole system of equations. This is equation in all the m variables, all possible kinds. Basically, what I am doing is the way to do this is first build a set of all tuples, k tuples of equations. Now, if anywhere, first in the first legitimate, we'll cross out things in which a variable appears multiple times. That's a very, very small fraction because k is small. K is a common. Think of k as constant compared to n. Then Then we go and look up, we go equation after equation, we look at a taken equation, there are two variables participating in it. Now we are asking, are these two variables going to appear in distinct equations in the set U? Notice the number of such things are really, really tiny. So I'm going to toss these guys also. And this is basically done. The reason this is done is there might be times, eventually I don't know if we come to that part at all. So not all the equations. So suppose we have this is more for the completeness setting. In the completeness setting, we have an assignment that satisfies 1 minus epsilon fraction of the equations. Now I would like to now extend that assignment to the set of k tuple assignments. Now, the natural way to do it will be, so the completeness will go by from 1 minus epsilon to 1 minus k epsilon. That is, we are hoping that those bad set of equations don't appear in any one of them. So that should have been fine, but later on we will shortly see we are going to be doing a folding. And actually, it's k epsilon, this won't suffice. We won't be able to extend this one. What we will show is, even though an invalid equation appears, it's not a built inconsistency over there. That is, there will only be two variables, there will be a third variable that's implied by this equation. You just set it locally for us answering this based on how it will satisfy this particular equation. You will, to see an inconsistency, you will have to possibly walk through a long cycle of equations. So in this case, we'll come to that shortly. So this is, and the reason you will see that when we come for the completeness. So this is, I'm going to have this impose the second property. And notice we also need to, so what am I going to do? So the eventual step is going to be, I'm going to look at this k equation. There are 3k variables. So now I'm going to look at a 3k dimensional subspace, and there's an n dimensional subspace we are working with totally. Every assignment is an n-bit function. We'll think of the n-bit function as so the global assignment is basically a function from n to 0, 1. We view this as a sigma a, which is a linear function from 0, 1 n to 0, 1, a linear function. Basically, in which x is being mapped to x. And the proof is going to basically use this linear function restricted to various dimensional subspaces. Now, what is the dimensional subspace that I'm going to give from the U side? U side, I'm basically going to take these k equations. Now, there are the k equations refer to 3k variables. Look at just the projection of the n-dimensional space to the set of these 3k. That is 0 everywhere outside the 3k guys and only on this. Let's look at just that 3k dimensional subspace. Look at all n-dimensional subspaces of this and give the restriction of the global assignment on all those n-dimensions.
So L is less than k.
Oh, L is so n is going to infinity, k is a constant. Now when k and L behavior, k is going off to infinity, L is a really small number compared to k. So this k is exactly the k on which the Grassmann test is going to be posed. So I'm now going to come up with that two-player game is changing to another two-player game, A and B. What is A? A is set of all U comma L. That's basically every guy is growing up into a cloud. What is the cloud? Firstly, U should be in the U which we said. It's one of these legitimate set of guys. L is in the Grassmannian of XU L. The XU is the 3k dimensional space when restricted to variables in U. But I'm not going to do that. But we also remember this is not sufficient. We need to also give an assignment that satisfies the k equations. So somehow we need to check that this linear function is a restriction of a linear function that satisfies this one. So what we will do is given for anything we define the space HU. What is HU? HU is just going to be the span of xi1 plus xi2 plus xi3, where E is of the form I1, I2, I3 and P. This is an element of U. So take every equation in U. It's basically an XOR of three variables equal to some P. Now, from those three variables, ignore the P for now. Construct the vector 1, 1, 1, 1 on these three coordinates and 0 elsewhere, and take the span of all of these. Notice our global linear function, if it satisfies this particular equation, when given this vector 0, 1, 1, 1, it should answer the function B. We need to check this. So what we will do, the way we will do is, if L ever intersects HU, we will not give it for all L's, but only for L's, so that L intersection HU is this one. So that from this L, we will extend it to HU. By this, HU will be set in this way, and you'll be able to validly extend it to HU. You follow what I mean? So certain the L's which are going to intersect HU, I'm going to drop out from this picture. The L's which don't intersect or intersect really, for those we'll give the assignments. Only those guys will give the assignments. And then, but from there, we will actually infer this L will be the space, we will infer on a larger space, which is basically going to be, we are going to take L plus HU, and we'll say that we know the linear function on L plus HU, given the linear function on L. There's only one way of extending it. The extension will be defined by the P vector. It's not formally defined, but should be clear. Given this, given a linear function on L, there exists a unique extension to L plus HU.
Where the equations are
Where the equations are satisfied. So that's going to be the left hand side. The left hand side is all these ways. The right hand side is going to be V and L prime.
Okay, this is small unit. This is small, the current element we are considering.
Yeah.
The current equations, not all the equations.
Yeah, it's E and U.
It's this current equation. This is the current equations that we are.
Yeah. So for a particular set U, I'm building the space HU.
You put the blow up.
Yeah. This is so I given U, which is a set of k equations. For that, I have to put a bunch of vector spaces L. Which vector spaces L I'm taking? Only those vector spaces that don't intersect HU. And what is HU? HU is the span of those ways. And this is V and V. And L prime is Grassmannian XV L minus. And XV is similarly defined. XV is exactly the space spanned by the variables in B. This could be a varying number, 3k minus 2 beta k. So it's roughly 3k minus 2 beta k, but it could be varying number. For each one of them, we take it and we put all the L minus 1 dimensions of spaces. Okay. And the edge is a very natural edge. I'm just going to pick a U at random from this. Basically, I'm going to pick k equations. If they are not legitimate, toss it out. If they are legitimate, pick that guy. And then from that, produce the V. The way we did by doing this beta, you land up with a V. And in a V, pick. So here from U, you first Let's write this. So I had to define that. I had to define what are the edges in this graph. It's the natural thing that is the edges in the graph is first pick u at random from u. That's the first thing. Then pick v from u by with this beta 1 minus beta point process. Pick a random L prime, rather pick a random L in A, sorry, pick a random L in G, GR, XU, L such that L intersection HU is this one. Pick one of these L's at random, and then you cannot do it this way. It's not going to be pick an L prime firstly in GR XV L minus 1. Then pick an L in GR XU L such that L contains L prime and L intersection HU is this one. Pick any such extension and then output UL VL prime as an edge.
But in item code, one of the L's is L prime.
One of the L is smaller. I don't know. By the way, slightly changed from last time. Last time we had a 2 to 2 theorem. This is a 2 to 1 theorem. I'm giving L's dimension of space on one side, L minus 1 dimension of space on one side. But you can just do this twice, come back to it, it will become a 2 to 2. So this is actually a stronger option. Both imply the other. It's a constraint, a 2 to 2 theorem that actually you had this particular shape. Then from that you can get a 2 to 1 theorem. What we are doing is we do the 2 to 1 theorem. Okay, and those are the edges. What are the constraints? Constraints should be obvious on this, no? So basically now I'm going to expect a labeling. I'm going to give a sigma from A to 0, 1 to the L, and this is a sigma A and a sigma B from B to 0, 1 to the L minus 1, where I'm going to view these as the L bit vector, the L minus 1 bit vector as linear functions on the corresponding L dimension and L minus 1 dimension spaces. So there are multiple things here. This L dimension space, once you get this, you extend it to. So once you get the space here, you extend it to HU using. You extend. So when you are given a sigma A for L, when you are given a sigma A of L, you firstly extend this sigma F. Yeah, this is now a linear function on a particular L dimensional space. You extend it to
L plus H.
Extend to L plus H, L plus HU. This is sigma A of U comma F. This is this pair. Therefore, you extend it to L plus HU, you can do that in a natural fashion, this one. Now, L prime is sitting over here. You ensure that L prime is going to evolve. L prime check that L prime is actually the same linear function. Is the restriction of this linear function to L prime. So and check So let's call this sigma A tilde, which is a linear function of this, and check sigma A tilde of L plus HU when restricted to L prime is actually sigma B of B comma. Okay. That's the test. And you can see it's a 2-to-1 test. Though this HU that is there, it seems as though there are several extensions. HU, there's only one way to extend it. There's only one extra dimension that you don't have. And therefore it's a 2-to-1 test. That's going to be the entire. Okay. So questions on there's something very glaring, we're not checking. How are we? Where are we checking the the edges being consistent? That is, so we have to do a little more. We have to fold.
Okay, if you take two L1, L2 for the same L prime, it increases by almost twice. Right?
What?
For a fixed L prime, if you take two random L1, L2, then the error increases by almost twice. Right? So doesn't that keep consistency state as well?
Okay, I have in the way I've said it, I have done it. So they are going to do one more thing over here. What they are going to do for the analysis, we are going to actually identify several things in the left hand side, plot them together. What are they going to plot them? So basically now we are going to fold A into a smaller set A prime. So basically what we're going to do is we are going to build an equivalence class in the left hand. Right hand side will remain as it is. Left hand side we'll identify, we'll build an equivalence class and then just make each of them into one particular single vertex. And then new edge between these two will be there will be an edge between this cloud and that one vertex, this equivalence class and that thing. If there was even one edge in the past, and the weight of this edge will be the sum of all the edges that go between that class and that one vertex.
And so this is basically saying you're ensuring the PCPs coordinates are equal.
Basically, I'm going to ensure that these coordinates are basically because I'm clubbing all of them, I'm ensuring that one way it is basically checking that the assignment here and here are all consistent. That is, all of these together are talking about the same linear function. I don't have to do more. And what is it that I'm going to learn? Basically what happens is if you have, so what we have, a particular things gives you for L plus HU. So you have a U1 and a U2. So this U1 you get it, and you get an assignment for L plus HU1, and then you get for L plus HU2. If these two differ only by HU1 or HU2 spaces, if one can be got from the other by just adding HU1 or HU2 to some elements of HU2, then a function here should completely specify a linear function there. That's what we'll say. What we will do is the following. We will identify UL.
So you really want to avoid consistency checks. That's
the whole point. So UL, we are going to identify them with this one. If L plus HU plus HU prime is equal to L prime plus HU prime plus HU. If these two happen, the point is, once I have an assignment to one particular guy, it uniquely sort of says what's the assignment to the other guy. So I need to check that these two are consistent. So basically what I'm going to do is I'm going to make them a single variable. Okay. For now, this is just to ensure so there are two ways to get around this. One is otherwise between these two, put a 1-1 unique constraint. Between these two guys, put a unique constraint to show that that's one, and have a 2-to-2 constraint. This way of doing it ensures that you don't have a mix of 1-1 and 2-to-2. The mix of 1-1 and 2-to-2 does suffice for the hardness purposes. It's just that it makes the problem ugly. This ensures that all the 1-1 constraints sort of disappear. I'm not going to bother much about folding. You can do this folding, it makes things a little complicated. And the reason for this folding, and the reason for the second argument over here, the second thing over here is basically to address folding. Now, notice that if you complete, let's just check completeness. Completeness, if I had not done complete, if I had not done folding, completeness, it's clear it's 1 minus k epsilon. Suppose the original assignment was 1 minus epsilon satisfied. The original gap 3 link 2 was 1 minus epsilon satisfiable. Completeness for the new object will be 1 minus k epsilon.
Where do you lose the k factor?
The k, you have shown that there are k equation, there's possibly epsilon equations that are unsatisfied, right? If you even pick, yeah, just
You
even
can only guarantee that one of those.
yeah. So if I had not done folding, that would have satisfied. Now that you have done folding, it's unclear if this can be done because you want in this entire cloud there not to be one of the parity equation. And this cloud could be really, it might be that there is no way that is every, if you're going to eliminate A, right? The 1 minus k epsilon comes from the fact that you have eliminated any, so there is a small set of variables, let's call it there's an m prime set of m prime set of equations which are not satisfied with the global assignment. We have originally we thought any u which contains even one such equation, we are going to not be able to answer it. And hence we get 1 minus k epsilon. But now if you go to say that every equivalence class that even has one of these, but the equivalence classes could, it might be that every equivalence class has this one. So what we want to do over here is that third constraint will, because of the way it is, will ensure that they might be not satisfied with this ones, but they are not satisfied because there's just one dangling isolated variable. You just set it not according to the global assignment, but what would have satisfied this constraint. And then show that the number of equations, number of u's for which such dangling things, that is the inconsistency of more than such dangling things are really small, and then you can handle it. So that's basically for this, you need to do the calculation. That's this extra thing over here. Okay, that's where we are. Okay, so now I would now like to, what I'm going to do is pull pointer. So we had this theorem. I want to now use this theorem to show at least on. I want to like to use this theorem to firstly show that in each most of the significantly a delta fraction we use. Suppose this test passes with probability greater than delta. I want to show that at least on a delta by 2 fraction of the use, what I have there is a Grassmann test that passes the Grassmann test well enough. Yeah, but the point is, notice that the Grassmann test is querying two things which are in the same side. And here you are querying two things on opposite sides. Question is, are these two really the same object? Now it so happens, so this is so far linearity was used, the only place we used linearity was for this to construct linear equations and to get this 2 to 1 property. This will be a next place where actually linearity will be used, rather the Hadamard coding is something called the covering property. We actually didn't do any of this. Covering property is an important thing that keeps coming up in the PCP construction. We didn't do covering in any of the reductions that we did, but let me tell you what covering is. Yeah, what we want covering property. Now when you define two distributions, L and N prime, the given on both on L dimensional subspaces of XU. So for a fixed u, which is a set of k equations, I'm going to define two ln l prime, two different distributions. One is going to be, so this was I started off writing it in one way, and that was not the way. So remember, the way I wrote this, initially thought I first pick L from this and then pick an L prime. But no, I decided to go with L prime this way. Ideally, I would have liked to pick L from Grassmann X, Grassmann XUL. So that's going to be, so these, basically L and L prime are going to be these two distributions. L is going to be pick L at random from GR X L. L prime is from V, from U, pick a V by this, using the coin, using the beta 1 minus beta coin process. And pick an L prime and an L at random from GR. This is XU, sorry, XV and L. Rather, these two are two different distributions. What I want to say is, because of the way V's are covered by U's, when I randomize over the choice of V, these two distributions will be very close to each other. You notice the thing is, when I pick a L this way, there is a possibility that when I pick L that way, there's a possibility. So suppose in a particular equation V you dropped off a variable. L that you dropped off a variable, L that you picked in the top way can contain two variables from the same equation. An L that you picked up from the bottom will, for a particular UV pair, this is certainly false. Because in a particular UV pair, if this V was obtained by dropping off two equations from a variable, this V will never contain a linear space in which would support on two variables from that equation. Whereas the L will construct. So just looking at these L's on the left hand side, you might be able to think that you can distinguish the L's that are coming from the right hand side. But what we want to say is actually, because this is linear functions, it's the Hadamard and Pote. Basically, what you're doing is linear function. What I want to claim is these two distributions are close to each other. It is leftover. Whether this is not always, so this is true for the Hadamard and for living linear functions. If I had gone to the sort of done the same thing instead of Grassmann XUL, I had gone for all L. Suppose these were just L bit vectors, and you went to L prime vectors, and you gave a function on this one and a function this way. This is not the same at all. Actually, they are order two. Firstly, dimensionally itself, they are of two different objects. I don't know how to say this correctly. That is, notice that each of the L's that are coming from the smaller thing are actually coming from a lower. Their entropy is smaller. The question is the entropy on V enough to push it back to the entropy in the original entropy? So the L's, if I fix a V, this certain L is coming from a much smaller. So if I fix for a fixed V, this L and that L are clearly distinguishable. So the point is that pumping of that extra V, is it enough to cope up with the extra entropy loss? First, you have to check that at the very least that should be true, and then you have to show that the statistical distance. In the case, because it's other linear function, this happens to be true. But given not linear function but a vector something else, this actually happens to be false. And this is the property of PCPs. When you're working with the Hadamard encoding that is used quite often, we didn't do any of those. It's several, in fact, one very important reduction where it is used is, which I didn't mention in class, is 3SAT. We showed 1 minus epsilon versus 7 by 8 plus epsilon. If you want to get 1 to 7 by 8 plus epsilon, you will need such a property. The thing which I'm going to be covering property is basically the fact that the covering property is the statistical distance between L and L prime is at most beta root k 2 power n plus 4. Well, k is the dimension of the ambient space, L is the
Beta is the same.
beta is the response. So you have to choose beta.
How do we think of this? It's small.
It's really tiny. This is, think of this as quantum and some. Eventually, we will assume that these two distributions are identical. So this is going to be an epsilon error. That is some error. Yeah. So basically, the beta is going to be chosen small enough such that these guys. So beta has to be exponentially small in L and polynomially small in B.
This is because you can upper bound the provision for
This is because to prove this, no, we haven't talked about this. This is from the correction from the past is not a hard thing to prove. It's easy to prove, but this is, I don't know, that's right. And this would not be useful for us. What we will need is, because eventually we are not going to apply L on this. There's going to be one zoom from below and one zoom from above, and you're only going to look at L's that are coming from a particular Q and W. And you want to say still this holds good. So actually, so you can still prove this. That is now including the zooms, zoom that is Q and W. For at least 1 minus root beta a to the 1/4 fraction of Q's, and for every W, that codimension of W is R, we have that SD LQW. By this I just mean L so that it contains Q and is contained in W, and similarly L prime QW is less than or equal to root beta a to the 1/4 2 to the L plus 5 to R L minus Q plus 5. This is basically running just a bunch of union bounds on the thing about it. All I want to say is you can choose beta such that these two guys look basically the same. That's all this is, the point of this. Writing up this. Why is the covering property useful? So right now, what I want to say is, notice that the test seems to be actually a test that's going across sides. But because of this property, you can think of it as the other query also coming. It's actually a L prime test on the same side. You can, because of this property, even though it's coming from these two sides, once you specify to an edge, it's coming. When you stick to a particular view, as you randomize over all the v's, and you do it, it seems as if you have a Grassmann test which is going on in one side. The covering property gives you this. So notice this is something which we did quite hard. This is a very clever trick that's going on the covering property. In the case of max cut, when we did compare it to max cut also it was the case UG was on a single. We took the UG which was just a single thing, but we had the max cut edges. Eventually, how did we run the UG? We ran it on the average of the function, and this is something very similar. That is, we are thinking of the covering property is sort of, even though the other query is being queried there, the two queries now are essentially queries on the same object. It lets you So you will apply. So because of this, there seems to be an underlying Grassmann test that is happening on XU, which is passing with a reasonable amount of probability. Delta probability. If the original test is passing with delta, the 2 to 2 test is passing with delta. At least delta by 2 fraction of the XUs are passing, the corresponding Grassmann tests are passing, and for each of them, you can give in a zoom lens. That's what's happening. Okay. And now we are going to use those zoom ins to actually construct a global strategy. Fortunately, now comes the problem which we were talking about before. The zoom in explains a very, very small part of the response. So that zoom in is not good enough, and you can't do this sort of what would we do? Peel. Next one zoom in, peel it off, and say there is only a constant fraction of such thing. Actually, a large fraction, and how large is it? That's where this lemma is going to come in. Picture what we're going to show. So this is going to be a modification of this. The Grassmann roundness. Basically, it's going to be a modification of this theorem that we had put up at the very beginning. So remember this theorem. We call this. I'm going to write something which looks very similar to what I will write. This is the formula. For all delta, there exists an integer r greater than 0 and epsilon greater than 0, 1. This is the same thing as before. And a function alpha going from the integers to integers, such that for all sufficiently large L and then k larger than L. So ideally, I would have wanted to say once I fix delta R, there exists a constant fraction of zoom in, zoom out that explains, and that constant will be depending on delta. Right now, I'm not going to get it dependent, I'm going to get alpha L fraction. That's where it's alpha L, so it will not be a bounded one, it's going to be alpha L. What we're going to get is the following numbers. If F Grassmann XUL to 0, 1 L satisfies probability L1, L2, FL1, L1 intersection L2, greater than delta. Then sorry, this is number between 0 and for at least alpha n is alpha fraction of q's. But if for alpha fraction of the zoom ins from below, there exists a W, that's a zoom from above, such that probability when you pick an N from Q, W, and there's a W and a linear function f on W, let's say f on W Yeah, it's a linear from W to 0, such that F restricted to L is F of L. That's it. And this is exactly the scaling argument, except that the scaling argument is going to go for a much longer period. It's going to go for alpha L steps rather than this one. And therefore, the usual way of doing it will not work. Usually, we take a union bound over it. That union, and usually we are okay taking that union bound because the number of L is independent of L. Here, it's not independent of L.
So you need some pairwise scaling.
No. So what they will do is a completely different thing. What they will say, and this is something which is part of the proof which I sort of see it step by step. What they do is, at this point, they say we will construct another test in which the two provers are also given Q along with them. And yet, and point is, once you give this Q, what's the number of L's that are eliminated? They say it's just because
You will depend on the share, right?
huh?
You will depend on the test.
No, so now is that they that's the test. Now let's say I'll give you another. Suppose the original test passed. Now they'll say a new test in which I also come up with a Q and send the Q across as part of the queries to the two variables. Previously, the variable I only given a UL and a VL. Now I give you a Q also to both the guys. The point is because they claim that and now you are only going to check them, and now they are only check on. You have to give a Q which is contained in the L. That's how you have to give a Q. And the claim is now now knowledge of Q gives a lot of information to the provers. They know that they are in this part of the world, but the claim they somehow seem to argue that this element, this only reduces the things. This reduces the error. So what they show. So what they're going to now. So they're going to say is the following. They're going to construct this. So right now, what was the two-prover game which we had? The two-prover game we had was you pick this U, you pick this V, you pick an L, you pick an L prime. You send one guy U comma L, and your other guy you send V comma L prime. And we are asking if this part, suppose this game passes, let's call this game pi. Probability of, suppose there's a strategy for the provers that pi accepts is greater than delta. They then say that what they want to say is they look at this other game. Seems very bizarre to do it because in the other case, if I give this object out, I lose completely. So I'm going to pick U, V, L, and L prime. And then I pick a Q which is contained in L prime. And I'm going to give U, L, and Q to this guy. And V, L, and Q prime to this guy.
What is Q prime? What is Q prime?
Sorry, Q. Sorry, I should have not said this. There's no, I'm not talking about an L at all over here. But no, but I'm going to forget about this test. This is not the test, this is the test which we have to analyze. I'm talking about this test. This test which we know already, in which U is given and V is given and we check. This way, this is just a parallel repetition, beta k parallel repetition, and we know the error goes on exponentially over here. Now what I will do, what they do is out here, I'm going to now pick UV and also Q contained in Grassmann XU of dimension Q. So there's alpha fraction of Q of dimension Q. And they're going to give U comma Q and V comma Q. The claim is, for some reason, they sort of say that we know, what do we know about this test? This test we know the probability of acceptance is, for what do we know about this test? We know for all prover strategies. For all prover strategies, probability of acceptance is at most exponential in minus beta k. This is what we have over here. What they claim is this revealing Q is going to give out some information, but yet probability acceptance over here is still exponential in minus k minus beta k by exponential in QL. It dampens by this factor, but that's a factor that I can afford. This is something which they say that giving this Q is going to reduce the space of this one, but it reduces by this. And hence, this is something I don't fully
K
know.
is really much larger than exponential in L.
Yeah. So these are all. K is much more
constant, so it's
Huh?
K is constant, so it's
K is also a constant, just like this is a super. Yeah. You should see that there are some places where they do write explicit constants in this paper. So there are like 10 per 9, and 10 per 15s, and 10 per 20s, and stuff, things correct. So basically, the vertex cover is hard enough when the number of vertices is more than the age of the universe or some such thing. That's what true in all of this. Yeah. Okay, so this is the part in it. But if this were true, now you can sort of handle it because each you just reveal out the Q. Still, it's not fully this one. What is the point is this theorem only tells you there exists a W. Question is, I would like this theorem in which I can compute both the alpha Q and W pairs are of this type. Fortunately, that's not true. Only this is true for every Q can. Now the question is, how do the provers agree on what is the W? Because only if Q and W agree, they know how to define. And actually, there could be a notice if a W is true, even smaller W's are true. If a W satisfies the hypothesis, a W of codimension 1 larger is also going to satisfy the hypothesis. So the W's are extremely large in number. There's no bound you can put on the W's. So now what they want to say is, suppose two W's are very good and they are very close to each other, then you can actually come up with a W which is the common, this one of them, which is also good. And then they will show that the number of maximal such W's you can put a bound on that.
So the upper cap.
The upper cap. But notice it's a very weird upper cap because if these two W's are good, it doesn't say the W that you build up is as good, at least as good. You can only say it is good to a certain extent, which might be weaker than this. So the caps are not sort of monotonic in how good they explain, but they sort of come up with some notion. They say for every threshold, so they have a particular this one. They say that these maximal W's they can put a bound on their size. Then it goes to the usual type of. That's what happens in this. So there's a lot of. I'll just take those lemmas and then we'll sort of conclude with this because. So they will prove this following. So they construct a Q list. It's a Q list of W's. So F is as before, it's a Grassmannian on XL to 0, 1 L. And tau prime, let this be a vector, which is basically tau 0, tau 1, tau r. This is things in 0, 1 to the r plus. And what is each tau y denote? Each tau y denotes if you get a W of codimension I, what fraction of the zooms Q to Wi are you explaining? That is the tower. Notice I would have liked this to be monotonically increasing this as what I mentioned, but they just count this one. We'll say for a subspace Q in Grassmann X U X sub Q, we'll say that the pair FW tau occurs with respect to Q and F if firstly if one codimension of W is I, which is some number between, it's a number less than or equal to R. So it is, I'm asking, so I have a particular zoom from below, and I want to ask what's the corresponding zoom from above? I know there is a zoom from above. I'll say that there is a zoom from above and a corresponding function f, so which such that this happens, and probability, then I pick an L from Q and W, Fl equals F restricted to L is at least tau L. That's all I get. This is just the definition of this point of time. Now, and we say a pair is maximal. The pair FW is maximal. So FW is explaining the zoom above, but explaining with W being codimension I. It's maximal if there does not exist any W prime which is larger than this, but its threshold is the corresponding tau L, that's all. The FW is maximal if there does not exist an F prime and W prime, so that several things should happen. W prime should be larger than W. And F prime, W prime, tau prime occurs. And furthermore, of course, you should have that F prime when restricted to W is actually equal to F. That is, it's a larger space. So in that sense, so if you give me a particular threshold vector tau, and in that sense, this is you can talk about a maximal object. And so we'll define this list tau prime Q of F is basically FW such that FW is maximum. And then the further modification of Grassmann's harmonious theorem is the following again. So the same statement for all delta, there exists constants Q, R, and the epsilon in 0, 1. That we set tau R to be epsilon and tau I to be 10 power minus 9 tau I plus 1 to the power 12. And we're going to set, so each tau I is going to fall by that factor. Then for all sufficiently large L, K greater than L, the following K greater than L, the following holds. One, if agreement F is greater than or equal to delta, that is basically F passes the test, then probability that when I pick Q from Grassmann XQ, this list of prime Q of F is not empty, is at least alpha. This is basically says that this for at least alpha and fraction of the Q's, there is a W that such thing happens. So this corresponding list will be non-empty. But furthermore, I need the fact that for all Q, list tau prime Q of F, this is not 2 largest x, this is 2 power Q, 2 power 8 R square L by epsilon to the power 2 power R. So this list, so now they will apply for this. Now they will do the usual list recording on. So the Q's they sort of handed over for this one, and this one is actually, and of course all the parameters are terrible over here, and the proof of this uses the sunflower lemma for linear subspaces. Not for linear subspaces. It's a clean statement, so I just put that statement also. In fact, that will be the clean statement we have seen in the last half an hour or so. Isn't it? It will be the cleanest statement. The statements are getting more and more gory because you have to handle this one. Then the proof is via sunflower lemma for subspaces. Basically says let F be a family of R-dimensional spaces. And size of F is n. Then I want to say the sunflower exists basically. And n, what is n? No, and m to the power 2 power r to the power r is less than or equal to n. Suppose this happens, then there exists m spaces in F. Say, let's call them y1, y2, ym, such that y is equal to y intersection yj. That is, take the intersections of all the j equals 1 to m. And basically, once you take this, so that's the core of the sunflower, and any two other pairs don't intersect anymore other than the core. That is, it says that if y is this one, if y is this, then yi intersection yj equals y for all I not equal to j. Basically, you have this. So what am I saying? If there's a large, if I want an m size sunflower, I want an m size sunflower of R subspaces, then you give me any set of n subspaces, n being larger than this quantity. That's the case, you can find any set of spaces that has m subspaces such that they form a sunflower. That is, if you take the intersection of all of them, then the basically the set looks very sunflowers. It looks like this. That's the only intersections are.
Yeah, how does this really compare with the normal sunflower? It's less than.
Well, no, these are subspaces, so it's a very different kind of this one. And I don't know.
It less than the actual sunflower.
It should be less than that. No. What do you mean? It should be, it's even more restrictive. So it should be,
Is
n should be even,
lesser than the original sample limits.
this bound n to the power r should be larger than the what say bound you have for the sunflower lamp.
So it's called yes, sample limits is for any set if
For any set. Should be lesser. Yeah, it should be lesser. It should be lesser. Yes.
Aren't you asking for more? Because
actually the
That
original
intersection-
sample conjecture, this is that thing exactly.
yi intersect yj equals to y, that's a statement about subspaces,
Yes.
not just elements. So nothing in the span of y's is
No, what? But as a string, it's just a state. These are all just intersections, no? There's nothing in the span.
It is free to each y as a state, then as a state includes like a sample that is.
That's all it is stating, no?
so the intersection yi intersect yj being y is as a set or as a linear space.
They are the same, no?
Yeah.
It's y plus w, which is has this one. Y intersection in yj is this. The set. It is the set intersection.
Okay.
Okay, it is set says 2 power at least.
So I don't recall. The point is, you could just invoke the what they say. You could just invoke the usual sunflower lemma. You get worse parameters than this. Because the subspaces, you get slightly better parameters. It's not that they require better parameters. Just that some exponentials are being replaced, some double exponentials are getting replaced by exponentials in their place. That's
That
it.
is constant.
Everything is a constant, each is a constant in a different one over here, so. That sort of concludes this, but of course, I haven't talked about the other part at all, that is the proof of the KMS2 thing. That's actually even hairier than this. It just, the part of the proof is you come up with this Grassmannian graph, you find out what is the eigenvectors of this.
One by Q power.
Huh?
Then that is good.
That's a well-known thing. The Grassmannian has this one. And now you do complete spectral in this world. You do a spectral decomposition. You write down the thing in this basis. You write the set in the indicator of set in this basis. Write it down, and then you bury this one, and you have and expand it out, and it works out. So the actual paper is long, and this one gives a survey of this calculations, and that runs 12 pages in this. It's a bunch of just calculations for this. So it's one. And both these together then complete them. That one might be worth looking at. The next one, to find out if there's a cleaner way to present this whole the KMS conjecture. This one I do not know which parts can be cleaned up or can it be completely done by another proof. Okay, but both are worth looking at. I will stop this right now. Thank you.